is current times resistance. So if you want to write it down. So you guys can see this like graphic. This guy's resistance and this guy's current, he's just trying to get through. Voltage is trying to push him. And resistance, based on how tightly he squeezes this, like the current is not going to be able to get through. So he's offering some sort of blockage to the path of current. So that's why it's called resistance. And voltage is just something that's trying to push the current through. If there's more voltage, what do you think? If there's more, this guy is like really strong, he's pushing this current. Is he going to go faster or slower? Faster? Exactly. And if this resistance is really, there's a lot of resistance, there's no place to go through. Like, is this I going to be fast or slow? Slow, exactly. So over here, now if say like resistance is 0, what's going to happen to the current? This is like simple math. So if V, you have a certain voltage. If R is 0, what's going to happen to the I? Any guesses? I will be 0 or I will be infinity?
If R is 0, then
if R is 0, what is going to happen to I?
I will be not.
So
yeah, so
good.
Wait, it doesn't have to be exactly 0. You can think of like R as like a really, really, really tiny number. So what would happen if you divide like say 5 by like a really, really small fraction?
It would be really big.
Really big.
Yeah, so we can say that it's like basically infinity.
And if R is infinity, like say R is like a really, really big number and voltage is something like 5 volts. Say if R is really big, what's going to happen to the I? It's going to go to 0, right? It's going to become small. So either of these cases are bad. You don't want like too much resistance and you don't want like absolutely no resistance. So yeah, so this is why Ohm's law is pretty important. It tells you a lot about what type of values to use in your circuits, what the behavior of the circuit is going to be. So that's something to really remember.
Yeah, so this equation here kind of also explains why we don't want a really high current. So the power consumed by whatever circuit you've built is equal to the current multiplied by the voltage. So especially in this case here where the resistance is way too small, the really big current is dangerous because that means that you're going to consume a lot of power in your circuit, which can lead to the circuit blowing up, or it can cause like a tiny fire, both of which are very unsafe. So we want to make sure to never use resistance values that are too small, or to not have a resistor at all.
Okay, so there's different ways you can connect different sources. Can everybody get off their laptops and their phones? Yeah. So basically, once we say something is connected in series, that means the same flow of current is passing through all these components. But when you say something is connected in parallel, you can see this wire goes here, but then it splits off into 2. And then it will join back and come to the center again. So can somebody tell me if this light bulb is broken, okay, and my circuit is on, what's going to happen to this light bulb? Is it going to stay on or stay off? Off. Exactly. So because this circuit gets broken, the circuit doesn't get completed. So there's nothing going through this light bulb. So, but in this one, what happens if this light bulb goes off? Is this one still going to be on? Yes, right? Because this current still has a path on the top, so it's still going to be a completed circuit. So it's generally advisable to keep if you have a lot of components, like a lot of motors, a lot of LEDs, you want to keep them in parallel so that in case one is broken or something like dysfunctioning, you know exactly where the problem is. Your other components keep working. Make sense? So do we like parallel more or series more? Parallel, right?
Okay, so at all of your tables, you should have like a thing in like a little, it looks like a little orange box, like this here. This is a multimeter, so you can use it to measure voltage and current. It's really useful for testing things out when you build your projects. But there's a correct way to use it. So for voltage, So say you have if you have like say a resistor and a breadboard, you can connect. Wait, sorry, I'm gonna steal your multimeter. So you can connect each of these to one leg of the resistor, and that means that this is gonna be connected in parallel, and you can read the voltage. However, for current, it's a little bit harder. So you want to put this in series in order to read current. So that means you're actually gonna have to break your circuit. Going back to the resistor example, you could like move one leg of the resistor out of your circuit, and then you're going to take these and use this to reconnect your circuit. So one is going to be like on that removed leg of the resistor, and this other one is going to go back into the circuit. So that means that this is like connected in series into your circuit.
Okay, so now in electronics, we have something called like a logic level. So you guys know all like computers are made up of ones and zeros. Like so in your electronic components, what does this component read as 1 and 0? Because even sensors act on 1 and 0s. So when we say a logic level is high or a signal is high, we say that it's 1. And then when we say the signal is low, we collapse it down to 0. So say that you're getting like some sort of signal, right, from your sensor. These are called analog signals, by the way. And your sensor is basically gonna translate, like, he doesn't know what all these numbers are, it's too complicated for him, so he's gonna be like, oh, if my signal is above a certain threshold, so like this whole part, I'm just gonna push it to 1, like, oh, this is 1. I don't care about like what exact value it is, I'm just gonna push it to 1. And everything below that, like this whole part, if it reads anything here, it's gonna push it to 0. Okay? So these values, this 1 and 0, they correspond to different voltages in your boards. So an Arduino board, which a lot of you guys are using in your projects, this one for an Arduino is like corresponds to 5 volts. So if a signal is on, it's gonna give out 5 volts. And if a signal is off, it's gonna give out 0 volts. And for a Raspberry Pi, like Sophia will talk about that.
A couple of common components that a lot of you guys are going to use in your project. So as mentioned earlier, the Arduinos are usually 5 volts, and then the ACO5, which is like a Bluetooth thing, if you guys have Bluetooth in your project, that's 3.3 volts. And similarly, Raspberry Pi and the ESP32 are also in 3.3 volts. And then most sensors that we use are going to be 5 volt logic level. So like there is some like difference between like the 5 volts and 3.3 volts. I'm going to go to fix that.
Okay, so this Arduino, like this sensor is an ultrasonic sensor which senses distance. This is a regular Arduino board. So this sensor utilizes 5 volt and 0 volt logic levels. And so does the Arduino. So can I connect these pins to the Arduino? Like no problem. Can I do that? If this uses the same logic levels as this, can I connect the two? Yes, right? I can.
However, the Raspberry Pi uses 3.3 volts, which is different than the ultrasound sensor, which uses 5 volts. So, does anyone see a problem here? Like, do we need to do something to fix this?
Because like if this Raspberry Pi only reads like up to 3.3. So if this sensor, for him high is over here. But for this Raspberry Pi, high might be over here. So you see how it's gonna misread the signal? It's gonna like categorize it in the wrong box, which we don't want. So you have to bring the signal down from 5 to 3.3 for the Raspberry Pi to read it. Does that make sense? Okay, so how would you like decrease this voltage? So we use something called a voltage divider.
Yeah, so for this voltage divider, we have like coming in is going to be what the sensor is sending. So in our case, that's gonna be 5 volts because our sensor sends 5 volts, or our sensor uses a 5 volt logic level. And then we're basically, and this symbol down here is the ground symbol, which means that at this very last point, after it's passed through resistor 1 and resistor 2, it's 0 volts. But we don't want 5 volts or 0 volts So we want to take a voltage in between the two resistors. Also, sorry, this picture is a little bit confusing. It's actually like resistor 1 is like its own resistor, and then resistor 2 is its own resistor. So you need two resistors. And then you want to take a point in between them, which goes to the Raspberry Pi, and in our case, we want this to be 3.3 volts. So essentially, we have this equation where V out, which is like the output, like the result of using this voltage divider, that is equal to this ratio between the two resistors. And then that's like that ratio multiplies V in. So with 5 volts and 3.3 volts, we're pretty lucky because 3.3 is like almost exactly 2/3 times 5. So that means that for the ratio of our two resistors, we just need a 2-to-1 ratio. So the actual values can be anything you pick as long as they're in a 1-to-2 ratio. However, we don't want to pick something too small. Say you pick 1 ohm and 2 ohms. We're going to go back to that problem that I talked about when we first introduced Ohm's law, where the resistance is really, really tiny compared to the voltage, and then your current will be way too high and things will not work. So typically we pick something like 10K and 20K for doing a voltage divider from 5 volts to 3.3 volts, and it usually works pretty well. And that's like the most common one, so you guys will probably be building that circuit.
Yeah, this is like really important if you're using a Raspberry Pi. Anybody using a Raspberry Pi in their projects, you should know how to use these. Anybody's using Bluetooth in their projects,